Hi, in this video we are going to talk about computation of power. We are given two numbers x and n. Our task is to compute x raised to the power n. Let's understand the problem with these examples. If x is 2 and n is 3, our result is going to be 2 raised to the power 3, which is 8. If x is 3 and n is 4, our result is going to be 3 raised to the power 4, which is 81. If n is 0, then our output is going to be 1. If n is 1, then our output is going to be same as x. Now please pause this video and try to write down a function that takes two numbers x and n and returns x raised to the power n. Let us first talk about a naive solution to solve the problem. The idea is simple. We initialize our result as 1. We run a loop to multiply the result with x n times. So we run a loop that runs n times, I equal to 0 to n minus 1, and in every iteration we simply multiply x with the result. So if x is 3 and n is 4, our result is initially 1. We are going to run this loop 4 times because n is 4, and we are going to multiply the result with 3 in every iteration. So after 4 iterations, our result will become 81 and we will return 81 at the end. The time complexity of the solution is clearly theta n because we are running a loop that runs n times. Now please pause this video and try to think of a solution that works in theta log n time complexity. Let us now talk about the idea for efficient solution. The idea is based on this fact that x raised to the power n can be written as x raised to the power n by 2 into x raised to the power n by 2 if n is even. And if n is odd, then we can write it as x raised to the power n minus 1 into x. So if you write the power in this form, you can notice that these two terms are identical. And if I compute one of those terms, I can compute the power. Now please pause this video and try to write a function which is based on this idea and which efficiently computes the power. Here is implementation of the efficient approach. We are following the same idea. We are computing x raised to the power n by 2, and then we are multiplying this temp with itself. We store the x raised to the power n by 2 in a variable temp and we multiply temp with temp. And then we handle the even odd cases. If n is even, then our result is simply temp, right? Which is x raised to the power n by 2 into x raised to the power n by 2. And if x is odd, then we need to multiply x one more time. Let us see the dry run of this code with this example. Say x is 3 and n is 5. So first thing we do is we compute temp equal to x raised to the power n by 2. We make a recursive call here. So our parent call 3 5 call stops here and it makes a call for 3 by 2. And when you make a call for 3 by 2, it again comes here, right, for n equal to 2 and x equal to 3. And it also does make a recursive call for x raised to the power n by 2. So it makes a call for 3 1. And this call again stops here and it makes a call for 3 0 because 1 by 2 is 0. And when you call for 3 0, it falls into the base case. When it falls into the base case, it simply returns 1 to the parent call. So the parent call, which was waiting for this to finish, now has temp equal to 1. So the 3 1 call has temp equal to 1 at this point. So what is it going to do? It's going to do 1 into 1. So it's going to get 1. And now n is odd, so it's going to return 1 into 3, which is 3. So it's going to return 3. This call is going to return 3, right? And now once it returns 3, the 3 is assigned to the temp variable in this call. And what this call is going to do, it's going to do 3 into 3 first, right? And n is even now, so it's simply going to return 3 into 3. That's what it returns. And when it returns 3 into 3, this is assigned to the temp variable in this call. And in this call, temp is now 9. So what it is going to do, it's going to first do temp equal to temp into temp. So it's going to do 3 into 3 multiplied by 3 into 3. And now it checks if n is even or odd. N is odd here. So what it's going to do, it's going to multiply one more 3. So that's your final result, which is 3 raised to the power 5. That's what we wanted. Let us now quickly analyze the time complexity of this solution. See, if you take a closer look at this implementation, we are making a recursive call for n by 2, right? Or you can say floor of n by 2, because if it's odd, then we call for n minus 1 by 2, right? So we make a call for n by 2 and then we do some constant amount of work. All that this work is constant. So we can write the time complexity as Tn equal to Tn by 2 floor plus theta 1 for constant. And if I draw the recursion tree, I'll get this way. Theta 1 work at the top, say n is 16, then you will be doing theta 1 for 16. then you will be doing theta 1 for n equal to 8, then theta 1 for n equal to 4, then 2, then 1. So what will be the height of this recursion tree? If you divide a number by 2 repeatedly, then the height that you get is log n, right? So the height of this tree is going to be log n, and at every level of this tree we do constant work. So log n into constant is log n. So overall time complexity of this solution is theta of log n. One thing about this efficient solution is it's a recursive solution. So it's going to have recursive function calls, and these recursive function calls are going to take space in the function call stack. And how big the recursion tree can be, how much can be the height of this? See, we have just talked about it. It's going to be theta log n. So we are going to need theta log n auxiliary space as well. Also, it's going to have overhead for the function call and return. In the next video, we are going to discuss an iterative solution that requires log n time and big O of one auxiliary space.